Okay, so now we're going to go over the kernel trick. So this is all a pretty general form for the kernel trick, and it's based off of the high-dimensional embedding that we described earlier. So with that in mind, let's let our zi be equal to our high-dimensional embedding of xi, right? And this is in our D, right? And so there's zik, for example, is equal to phi sub k of xi. So now we're going to envision, let's just hypothetically make these transformations using this high-dimensional embedding. And then now we're going to think of the zi as our new feature vector, and we're going to apply a linear method. And we're just going to see analytically what this is doing. So for example, let's consider linear SVMs. Linear SVMs, support vector machines. So if we recall, this is for our yi, which is in -1 or 1. If we recall, we're trying to minimize with respect to selection of beta our, and this is in RD, we're going to imagine that we've either included an intercept term in the high-dimensional embedding, or we don't care about having an intercept term. So this is the sum, I going from 1 to n, of 1 minus yi times, we could write it beta transpose zi. The positive part, this is the hinge loss, plus our lambda times beta 2 norm squared. Right? So let's consider these two terms separately. Right? This is term 1 and term 2. Right? Okay. Okay, so the basic thing that we can note is that term 1 is dependent on our zi, but term 2 is not dependent on zi. So that's the first thing to note. And we can make a claim, which we're going to verify. So our claim is that beta hat solves that solves the SVM, the beta hat which solves the SVM, so the solution can be written without loss of generality. Z transpose alpha for some alpha in our n, right? Which the way we can think about this is beta hat j, the jth component of this, is equal to capital Zj transpose alpha, where this is a column of the new design matrix. And our capital Z here, this is our our capital Z, this is our n by capital D design matrix. Okay. So it can be written in that way, which we can further write this as the sum over I alpha I times Zij, which another way to write this is the sum over I alpha I times Zi, where these are rows of Z sub j. So there's a couple of different ways to write this. But what this means is that the beta is some linear combination of the z's, of the columns of z's, and that's that was true of ordinary least squares, for example. But then, or sorry, So that's a claim. And we're going to verify it right now, and then we'll see what that implies later on, right? So another way to write this claim is that beta hat lies within the row space of Z. That's another claim here. That's another way to think about this. Okay, so let's prove this claim. proof. So first of all, let's just write our beta as some linear combination, sum over alpha I, zi, plus some component which we're going to call beta orthogonal. We can always do this because zi, furthermore, zi transpose beta orthogonal is equal to 0 for all I. We can do this just because zi, the span of zi, of the zi's, I going from 1 to n, this is some subspace in Rd, right? And so we can decompose any vector as one component which is in the subspace and another component which is orthogonal to the subspace. So this can be done for any vector, it can be done for beta as well. Okay, so let's look at what zi transpose beta is. Then, if we write it out in this form, well, this is the sum over j. Let's just write this out. Expand out our new form of beta. Alpha j times zi transpose zj, right? Where these are rows of z. Okay, plus our zi transpose beta orthogonal, but again, this is equal to 0. Just because of the way that we selected the orthogonal component of beta. Okay, so far so good. And this is equal to our zi, our row, transpose capital Z transpose alpha. It's another way to write this. That's just linear algebra. And so if we think about our objective, we can see that this implies that our beta orthogonal does not impact the first term here, the data-driven objective. Right? The hinge loss is not impacted by the selection of beta orthogonal. Right? Now let's look at the impact of the beta orthogonal component on the regularizer term, this ridge regularization term. Let's look at that. So we have beta 2 norm squared. We can write this out as the Z transpose alpha. That's just another expression for beta for this term here. This term here is also capital Z transpose alpha. That's another way to write that. Right? And then this plus the beta orthogonal component, right, squared. But that's just equal, if we expand out this 2 norm to Z transpose alpha, 2 norm squared plus 2 times beta orthogonal transpose Z transpose alpha, right, plus the 2 norm of beta orthogonal squared. Right? But this term here is going to go to 0 because this is equal to alpha transpose Z beta orthogonal, and this is equal to 0, this term here. Right? Sorry, without the 2. We can write the 2 there. That's equal to 0 just by assumption about beta orthogonal. Right? So the remainder of this is equal to this Z transpose alpha plus beta orthogonal. Oh, sorry, the 2 norm squared plus the 2 norm of beta orthogonal squared. 2 norm squared. All right? And so this is equal to, or this implies that beta orthogonal at the minimizer is equal to 0. Right? Because let's look at what the objective now becomes. We have one component, this first component, which has no dependence on beta orthogonal. Then the second component can be written as the sum of something that depends on alpha and something that depends only on beta orthogonal. And that something is this 2 norm. So to make it as small as possible, we just set that 2 norm to 0, and the only thing that's going to allow that 2 norm to be 0 is by setting beta orthogonal to be 0. So beta orthogonal at the minimizer has to be 0. Okay, so we have that, and that is a fact about linear SVMs. So now we can just rewrite linear SVMs using this claim. So the claim is proven that the beta hat, which solves SVMs, can be written as Z transpose alpha. Right? So let's just plug that in. Now we're trying to find this alpha instead of the beta. And alpha is in Rn, whereas beta was in Rd. Now D, capital D, could be bigger than N. There's nothing stopping us from doing that. Okay? So let's see what happens now when we rewrite the support vector machines, linear support vector machines here. So we're minimizing with respect to alpha, selection of alpha, which is in Rn. This 1 over n, sum over I, 1 minus yi, times our zi transpose beta, and beta is Z transpose alpha. Right? Positive part, it's the hinge loss, plus lambda times Z transpose alpha squared. Right? And that's just because we've plugged in beta hat is equal to capital Z transpose alpha based on our claim. Okay, so far so good. Now, the interesting thing about this is that, first of all, very little actually depended on the details of the support vector machines. We required a hinge loss, and we required a loss that only depended on Zi transpose beta. So that's actually a quite general form. So let's write it out as a general form, and then we'll see what this has to do with kernels. Okay. So first of all, our general form is we're going to minimize with respect to beta, which is in Rd. So this is the general form. Minimize with respect to beta in Rd, Rn of some empirical risk of y times z times beta of z times beta. So it's some function of y, whatever it is, and then its only dependence on beta is through z, right? Through z beta, plus lambda times the 2 norm of beta squared. We can follow the same logic as we had before, right? The only thing we required is that the first objective had only a dependence on beta through z beta. Then we knew that movements in that orthogonal component had no change on that first element, and then the only thing that changed was the 2 norm, and to minimize it we would set the orthogonal component to 0. So that's the first thing. So this is our general form, and anything that can be written in this form would satisfy would allow the kernel trick. So this would include logistic regression with the ridge penalty, and it would also include ridge regularized linear regression. It would also include that. So this is important to note that this is quite general. It's not even specific to binary classification. So this is equivalent by the claim to minimizing over alpha in Rn of the same risk over y, but now instead of z beta, it's some matrix K times alpha plus lambda alpha transpose K alpha. And this is called the kernel trick. And I'll describe what K is. This equivalence is called the kernel trick. And I'll describe what K is. K is just equal to it's equal to Z transpose, right? Because here, this is Z transpose alpha sub I. That's what this is here, right? And then, and so this is only dependent on K alpha. And this term here, we can write this as alpha times Z transpose alpha, alpha transpose Z transpose alpha. And so this term is alpha transpose K alpha. And this is called the kernel matrix. Okay, so the kernel trick just says that these two optimizations are equivalent, right? All well and good. Why do we care about this? Well, if you think about what the elements of K are, then it becomes apparent that this is actually a really nice fact computationally. So Kij, this is equal to Zi transpose Zj, right? But this, remember what Z was. Z is a high dimensional embedding of Xi transpose V Xj. Some high dimensional embedding of Xi. And so all we needed to form this K matrix were these inner products. Right? So this actually implies a second way to solve this ridge regularization term, this ridge regularization problem. So method one is we define a high dimensional embedding and use it, right? We apply it and to get Z and solve, or apply it and then solve. Let's just call this 1. Right? Method 2. So that's one approach, and that's the approach you take when you do features construction, when you take logs and squares and basis expansions of X variables, and then apply your favorite linear method. That's the method that you might be accustomed to. The other approach is to instead think about a kernel function, which is just a name for this function here. Xi, Xj. Right? So method 2 is to define a kernel function and that's this K of x1, x2, which is equal to phi of x1 transpose phi of x2. So that's the other approach. And then we can compute K, and we can do this in many circumstances. We can do this in closed form. We can think about just analytically, what is the high dimensional embedding? Let's analytically figure out what an inner product between the high dimensional embedding at two different points is, and then write out this kernel explicitly in closed form, and then we can compute the similarities based on this kernel function between x1 and x2 for every point in our data set. And so then we compute capital K according to this equation star. So what's an example of this? Actually, before we go on, let's just think about how we go from a solution to 2. So now when we solve equation 2, if you look at equation 2, that's this kernel trick program. Right? If we solve equation 2, what we end up getting is alpha. Right? This results in alpha hat. Right? Okay, great. And then from there we can get back our betas if we want. And beta hat is connected to alpha based on z. Now, you don't always have the luxury of doing this because you don't always have access to z. Like I said before, you can just construct this kernel function in closed form. Analytically, you can think about how can I evaluate this kernel and then compute this K matrix. Once I have this K matrix, I can solve problem 2. I don't need z to do that. But if you did need to convert to the beta, you would need to construct z and apply z transpose to alpha. Okay, now how do we do predict? We don't actually want to compute this beta hat, right? So this can be avoided. I'm going to say that computation of z at all can be avoided if you have this closed form for this inner product. It can be avoided because when we go to predict, it looks like the following thing, right? If we had access to beta hat, then what we would do when we predicted is we would take a new z, apply our high dimensional embedding, we would take it, transpose beta hat, and that would be our new decision function, right? But let's think about what this is. That's equal to phi of x times sum over I, alpha hat I, zi, right? But that's equal to sum over I, alpha hat I, phi of x, transpose zi, but zi is phi of xi, right? So that's equal to sum over I, alpha hat I, times this k between x and xi. And so we can do predict also. We can evaluate our decision function if we just have access to the kernel function. We don't actually need to construct the z's again, and we don't actually need beta hat to do this. We just need the alphas and a way to evaluate our kernel function. So everything here can be done just through evaluation of the kernel function. So let's think about an example here. This is called the nth degree polynomial kernel. And our kernel function, this is one example where the kernel function is really easy to evaluate. It's 1 plus x transpose x to the d. Transpose x prime to the d. So if I was given, so I'm going to propose a kernel. So this is sort of the opposite of what the narrative, what we've been going through, where we say that we have some high-dimensional embedding that has an inner product between two high-dimensional embeddings, and that defines a kernel. We're going to sort of think of it in the opposite direction. We have a kernel. What's the high-dimensional embedding that corresponds to that kernel? Well, let's think about d equals 2. And d equals 2, if we just evaluate this, we get that it's 1 plus x1 times x1 prime plus x2 times x2 prime, where this index now corresponds to the coordinate. So this is the first coordinate, second coordinate, and this is squared. Right? So let's think about this. This is equal to 1 plus 2 times x1 times x1 prime plus 2 times x2 times x2 prime plus a bunch of other terms. x1 squared times x1 prime squared plus x2 squared plus times x2 prime squared plus 2 x1 x1 prime x2 x2 prime, right? So we have all of these terms. Now how can we write this as an inner product between two vectors? Well, this is equal to the inner product of 1 root 2 x1 root 2 x2 root 2 x1 x2 x1 squared and x2 squared transpose the same thing but for x prime. Right? Because if you look at it, you have the 1 times 1 is this one, root 2x1 times root 2x prime 1 is this one, and so on. So this kernel that I've written out here, this kernel, is the inner product between these two vectors, right? But to evaluate this kernel, all we had to do was take the inner product between x and x prime, whereas to evaluate this inner product, we would have to do this embedding, this following embedding here, and then take inner products. Now, actually, it might be still computationally easier to take the higher dimensional embedding than to evaluate these kernels, because alpha is in our n, if n is much bigger than the number of dimensions. But you can imagine if we increase the degree of this polynomial, or if we increase the number of dimensions, then the size of this, the capital D, the high dimensional embedding space, is going to get very large very quickly. Right? So it very well may be that our high dimensional embedding space has capital D dimensions much larger than the number of sample points, in which case it would be computationally advantageous to work with just the kernel functions and evaluate this this optimization program, the Kernel Tricks optimization program number 2 here. Okay, so this can be a bit confusing. The basic idea is that our there were sort of two ways of going about creating nonlinear decision boundaries from linear ones. The first one was applying a high dimensional embedding and then thinking about linear decision boundaries in that high dimensional space. When we do that, then we end up getting a nonlinear decision boundary in the original space. And we saw that before. Now, it turns out what the kernel trick says is that it turns out that we can solve either of these two optimizations, whichever is the most convenient for us. Right? And I'm not saying right away what's obviously going to be more convenient for us to do. But the interesting thing is that the kernel trick, it is a way of solving this without ever actually applying this high dimensional embedding. And so if you have some high dimensional embedding in mind, then you could, in some instances, figure out in closed form what the kernel is, which is this inner product between the two high dimensional embeddings. And then given that kernel function, you can evaluate what the kernel is between all of your pairs of data points, and then you could solve problem 2 here. And we've already shown that you can do the predict step. You can evaluate your decision function if you have this alpha and access to the kernel function. And so we've sort of circumvented this construction of the high dimensional embedding. Now we're going to take this narrative to a greater extreme by showing that we can propose kernel functions just based on some notion of similarity, and we don't even have to have some high dimensional embedding in mind. And it turns out there will exist some high dimensional embedding for kernels that satisfy basic properties called Mercer kernels. So that's going to be the next step, is instead of thinking about high dimensional embeddings, we're just going to think about kernel functions only, right? And you can think of a kernel as a similarity. The larger it is, the more similar you think x1 and x2 are. And then we are going to gain a lot more freedom in terms of creating nonlinear classification methods and regression methods by thinking of kernel machines. So we'll talk about that in the next video.